Dear participants, welcome to our seminar organized by the Istanbul branch of the Turkish Chamber of Civil Engineers. Today, we are holding the first of international seminars. The seminars aim to bring together prestigious engineers, academicians, and experts from all around the world with you. The seminars, which will be published on eğitim.imoistanbul.org with the option of original language and Turkish translation, will convey to you the new technologies and important research about our professions in the world. The topic of our seminar today is Digital Concrete Enabling New Processing Technologies for Construction, and its lecturer, Dr. Timothy Wangler. The seminar is going to be moderated by Professor Nilüfer Özyurt Zihnioğlu. We would like to thank Mrs. Zihnioğlu for her moderation and Mr. Wangler for his presentation in advance. You can send your questions from the live chat section of YouTube or education system. Now I'm going to hand you over to dear Mrs. Zihnioğlu.
Thank you, Damla Hanım. Dear guests, good evening. I also would like to welcome all of you on behalf of the Turkish Chamber of Civil Engineers. Today, we are gathered on that platform to listen to Dr. Tim Wangler, who is one of the most pioneering researchers in the field of digital concrete. Before I give the word to Dr. Wangler, I would like to introduce him and his work on construction materials. Dr. Wangler is a senior researcher in the chair of physical chemistry of building materials, Institute for Building Materials at ETH Zurich. Prior to his current appointment, he was a postdoctoral researcher and senior research assistant within the same chair. He received his bachelor degree in chemical engineering from the New Mexico Institute of Mining and Technology in 2001 and worked for some years at Intel's semiconductor manufacturing facility in New Mexico before starting his PhD studies in Princeton University. He received his PhD in chemical engineering from Princeton University in 2009 under the supervision of Professor George Schrader on the topic of swelling clay minerals in cultural heritage stones. Following this, he had a postdoctoral appointment in IMPA, the Swiss Federal Labs for Material Science and Technology, to study the release of biocides from facade coatings. In 2012, he joined Professor Robert Flatt's chair in the Institute for Building Materials and has researched a variety of topics related to the broad area of organic, inorganic surface interactions in construction materials, including the topic of recent high-interest digital fabrication processes with concrete, including 3D printing, with a focus on cement hydration control. Now, I know our guests are impatient to listen to Dr. Wangler's talk. Therefore, I will soon give the word to him to give his talk on digital concrete. But I would like to just make one last point. I believe in the end of his seminar, we will have a fruitful questions and answer session. So one more time, I would like to remind our guests to ask their questions via live chat, and I will direct your questions to Dr. Wangler by the end of his seminar. Dear Tim, the floor is yours.
Okay, thank you very much, Nilüfer. Now I will share my screen for the presentation. Thank you very much, and thank you for the introduction. And it's really an honor, and I thank you for this invitation to give this lecture and this seminar. It's really wonderful that we can do this online via Zoom, as we're all used to by now. Although I much prefer to do these types of things in person. I still have fond memories of speaking in Bursa 2 years ago, especially of the kebab Iskandar. But enough of that. Now it's time to discuss digital concrete and the real topic of my seminar. I won't go into much detail because of the nice introduction about where I'm coming from, but I'm coming from the Chair of Physical Chemistry of Building Materials at ETH Zurich. It's headed by Professor Robert Flatt, who's a world expert, of course, in chemical admixtures, especially superplasticizers. We have a rather large team, and of course, as I mentioned, a strong competence in chemical admixtures, which is in fact one of the most important aspects of research in digital fabrication with concrete. The team, with respect, actually, it's about half of the research group's focus is on digital fabrication with concrete, with some faces that are involved or recently involved, seen here in this slide. So it's quite a wonderful topic for us for the past few years, with a lot of things going on, especially thanks to the National Center of Competence in Research, which started in 2014. It's a 12-year funded program that we are one of the participants of. It's the largest funding mechanism from the Swiss National Science Foundation. And it was an initiative really to foster architecture and construction and digital technologies, and to bring these together with many, many different researchers, all brought together in an interdisciplinary center. What you see in this photo here is our robotic fabrication lab. This was actually taken at the very beginning when it was very empty, but this lab has been full for many years with many different demonstrations of digital fabrication in architecture, not just 3D printing with concrete, but also things related to timber and other types of technologies. My talk will be just to give a brief overview on first answering the question of why this is such a hot topic. Certainly within the past few years, it has just exploded in research interest. Before I get into the approaches that we take at ETH Zurich, or the technologies that have been developed at ETH Zurich, it's not just 3D printing, but other forms. And then I'll discuss the different types of material and processing challenges before I give an outlook. And I want to focus on a couple of things, especially related to why we're doing what we're doing, especially as it relates to issues of sustainability and productivity in the construction sector. So this is actually it's a little bit old, this collage of photos showing all the different demonstrations. You can see, of course, some of the pioneers here. This is Dr. Barak Kushnevnis, who really came up with and brought to the forefront the concept of 3D printing with concrete, which he called contour crafting, and another pioneer here, Enrico Dini. But many recognizable demonstrations can be seen here. 3D printed bridge here from China. This is a 3D printed bridge from the team in TU Eindhoven, as well as other houses from China, Dubai, and in the United States, and including us. We in ETH Zurich and our NCCR, we have created the DFAB house, which I'll discuss later in this talk. So I often like to talk or to introduce or at least include this slide, which is something called the Gartner hype cycle. The Gartner hype cycle is a kind of descriptive curve of how technology evolves. A new technology first has some trigger, it explodes onto the scene, and everyone believes it will save the world. So everyone believes that this is the newest and greatest technology before it reaches this peak of expectations, which are just too high, and everyone realizes that this new technology won't save the world, and it comes crashing back to Earth in this so-called trough of disillusionment before entering what's called the slope of enlightenment. And this hype cycle has been generated for many different types of technologies, including 3D printing. And I believe that our little section of 3D printing with concrete can be included in here as well, in the top here in macro 3D printing. But keep in mind, this is in 2018, this one. And I believe that we're starting to fall down here in somewhere in this region by now, because while there's a lot of hype for it, there's also a currently lack of very big market penetration. This will probably take some time before it gets to that point. Okay, so why the hype? This hype actually has led to many different misconceptions where probably you have seen in the news that so-and-so company has claimed to 3D print a building in 24 hours. And as a matter of fact, this was a study done by the major 3D printing company Cobod, based out of Denmark. So they're a company too, so they of course have their own agenda. But they really looked for the truth in this, and they discovered that nobody has 3D printed a building in 24 hours. They have changed the words to say that we have just using print time, for example, but it's still a major challenge to actually 3D print a building in 24 hours. Not to mention that a building is a lot more than just the concrete vertical walls. It's many different aspects go into a building besides just the walls. But even the walls have not been 3D printed in 24 hours. So many challenges still are remaining, which we'll discuss. So why all this hype? It's worth asking, what problem are we trying to solve with this technology? What is it really good for? And what we at ETH Zurich believe that its main promise is in increasing sustainability. While many are attracted to its increase in productivity. So we think that it has the chance to reduce the, environmental footprint of concrete. And there's also the idea that it can increase the speed of construction. So let's focus on the sustainability case. Well, what does 3D printing bring you? It brings you shape freedom. Essentially, it gives you what you could say is complexity at a lower cost. So you can produce bespoke or unique elements without paying for very expensive processes to create them. To give an example seen here, this is a slab element that was using a topological optimization algorithm for a specific loading case. Material was removed from this so that it could still support the load with up to 70% reduction in concrete. So the idea being that you're putting material only where it's needed. And if you're putting material only where it's needed to create this complex shape, how are you going to create this complex shape? It turns out that to create this complex shape, you need a method which can create these complex shapes at a lower cost, because until now, architecture really is limited more by the economics of construction rather than by physics. It's limited because of the construction of formwork, and formwork forms up to 50 or more than half of the cost of many standard constructions. And the moment that, so this forms really the big share of the costs in construction with concrete, formwork labor especially. And when you want to create a unique construction, this is an example of the Rolex Center in the EPFL, our sister institution in Lausanne in Switzerland, which is a beautiful undulating building. And when you want to create a unique structure like this, you have to first create a lot of specialized formworks. And these specialized formworks eventually end up as just a mountain of trash. So it's a very wasteful and expensive process to create unique shapes. So the moment you become non-standard, your costs increase dramatically. Now, on the other side, the side of productivity, here we see that productivity in the manufacturing sector has nearly doubled, whereas in construction it has remained flat. So probably you have seen some variation of this type of plot at some point, indicating the problems related to the construction industry. You can even see in the past 15 years, it's actually even decreased. So why is there this huge gap between the other sectors? As you can see in this plot, agriculture has really exploded in productivity compared to construction, which is just lagging overall. And here we see manufacturing again. This is a very big issue because engineering and construction, or the architecture, engineering and construction sector, is 6% of global GDP. And it is the #1 consumer of all raw materials in the world. So greater productivity would be a wonderful thing for the construction sector to realize. Additionally, and especially in the developed world, there is a major skills or a labor shortage that has struck. This plot here shows from Turner and Townsend where there are labor shortages throughout the world, and you can see that in 60% of cities. This is again from 2018, but this data has not changed much in the past 3 to 4 years. The major cities of the world are all suffering from a labor skills shortage. Many of these construction jobs are considered as undesirable in these areas, too dangerous, and as a result, it's very difficult to find workers, even for many standard jobs, as maybe you've seen in the news in the United States. It's very difficult to staff. Another major problem affecting the construction sector, which is probably related to its very low amount of productivity, has to do with its level of digitalization. This is from the McKinsey Global Institute, where they created a digitization index showing the level of digitization in different sectors of the economy. So as you can imagine, things like media are very, very well digitized, and even manufacturing quite well digitized. But down here at the bottom is construction, just above agriculture and hunting. So construction really suffers from a digitization gap, you could say. So the vision to address all this has to do with, let's say the chain of events that occur in a construction's lifetime. The first comes the planning, then you have the design, then you have the construction of the whatever your building is in question, the building or construction structure, whatever, has to be in operation until it reaches its end of life. And the idea behind the use of digital fabrication technologies is to merge these first 3 steps, the planning, the design, and the construction, to make this much more efficient. Once these are much more efficient, then this will help to reduce costs and increase productivity. just going on from that previous slide, the idea here is seeing the relative costs of a change in a construction from the planning, designing, building, and operation stages. The greater you, or let's say the more you change or shift your modifications to your construction to the planning and the design stage, when things are just virtual, either on paper or hopefully in a digital form in the now or in the future, then your costs decrease significantly. Okay, so one of the questions I want to answer at the end is, are these two cases, are these two reasons for doing this technology, are they compatible? And we'll come back to that in the end of the seminar. So now I want to discuss the methods that we've developed in ETH Zurich, you know, we've developed quite a lot of methods, but also many others have developed them as well. At ETH Zurich, I mentioned earlier the demonstration. It's something called the DFAB house. This is a house that is located in Dübendorf at the EMPA campus in Dübendorf, Switzerland, at a building called Nest, which is a series of slabs where you can test different construction technologies in a modular fashion. And we tested the construction of this so-called DFAB house, which contains different elements, or we call them innovation items, related to some digital fabrication technology. So what you saw on the top were robotically fabricated timber units with a translucent facade containing a special aerogel insulation, and then there is a so-called smart slab, which is from 3D printed formworks. The facade, which is a clear facade supported by different mullions or columns, were produced by our technology Smart Dynamic Casting. There is a undulating wall in the center, which is produced through the mesh mold technology, which I'll describe soon. And this is a picture of the three main concrete technologies: the mesh mold wall, slab on top, and the Smart Dynamic Casting facade mullions. So these are the different technologies that have been developed at ETH Zurich. I mentioned Smart Dynamic Casting, which is a slip forming technology. We have technology we call digital casting, concrete extrusion or 3D printing, which is what everyone is familiar with. And then the mesh mold and knitcrete, which I'll discuss as well. So first, I would like to talk about the mesh mold technology. So the idea behind the mesh mold technology is to robotically produce a mesh which acts both as a formwork and a reinforcement. So it's essentially the construction of a functional formwork, which is a very promising type of technology. So what we have on the mesh mold wall, or in the mesh mold technology, is this so-called in situ fabricator. So this is a mobile robot, and this mobile robot can position itself, and through positioning sensors, position the tool head of the robotic arm that is mounted on the in situ fabricator. And this tool head can bend, cut, and weld steel together. So it's essentially stitching together in a specific shape steel reinforcement bars. So these steel reinforcement bars are stitched together to form this wall, and then the tricky part, at least the part where we come in, well, the tricky part is actually the construction of the steel cage. It's also tricky to put the concrete in, and that's what we did. But it essentially is the pumping in from the side of a pumpable. Actually, it's more of a fine-grained mortar because it was easier to put it inside this before it was then finished. Slip forming is a technology that was really the technology that brought us into the digital fabrication with concrete space. It was pioneered by Dr. Ena Yoret, who is seen here. And the idea behind slip forming is where you take a formwork, which is much smaller than the element being produced, and you put concrete into the top of the formwork, and it's very fluid. And then as it's moving up in time and rotating and forming deformations and changing shape as well, it is hardening the moment it comes out of the bottom of the formwork. So this obviously relies on hydration control, or the control of the hardening process. And that was really the key element for this technology. And also the key element of every technology related to digital concrete is this hydration control process, which I'll discuss. So one of the best things about this process in our mind is the ability to integrate standard reinforcement. So what you see in this video here is the production of one of these facade mullions. These are the columns that were used to support the facade elements. And as the formwork slips up, it can change its shape to put the material in the center of the, because the main loads that these columns will be bearing is wind loads. And so the major compressive loads will be in the center of the column, and therefore that's where you need most of the material. And as I mentioned, one of the major reasons we like this technology is because it integrates standard reinforcement. You'll see that with 3D printing of concrete, it's very difficult to integrate reinforcement in any kind of a meaningful way. Coming from smart dynamic casting is what we call digital casting or digital casting technologies. And in this technology, we basically use the key technological, advancement or the key technology of smart dynamic casting, which is control of the hydration, to control it in the case of the formation of, or the filling of weak formworks. And really 3D printed formwork. So I'll play a video here for you. So because of the formwork pressure, the formwork breaks. Because these are 3D printed plastic formworks, basically. But with the eggshell technology or the hydration control technology, you can fill these types of formworks without breaking the formwork. So this includes, of course, the eggshell process, but we can also use it to fill any kind of formwork that you can dream of and just construct. And in this case, to make a folded structure, the student here, Anasabo, she made she just took 2 plastic foils to create the shape that she wanted, and then filled the formwork using the set-on-demand or hydration control technology to control it so that it didn't receive too many deformations. And that's really one of the key, promising technologies we see is this hydration control technology to fill non-standard formworks. In fact, most recently, it's been used to fill formworks made from paper. So last but not least is concrete extrusion or 3D printing with concrete. This is, of course, the technology that most everybody is familiar with until now. Because it's the technology that is 90 to 95% of the research, and also probably with the most market promise, at least until now. And under the context of a project that's called Concrete Choreography, I can describe to you our system. So we 3D printed for an art foundation in Graubünden in Switzerland. For an art festival, 9 columns for a dancing stage. So these were digitally designed columns. The students had to first take the digital designs or create them, and then they had to turn these digital designs into something that the printer could create. And then they were printed. And the printing is done at a vertical print rate of about at least 1 meter per hour. And it's done through a set-on-demand technology, which I'll describe. Again, it's all related to hydration control. Now, as you saw, there's no reinforcement until now. It's because the print head doesn't really allow the easy integration of reinforcement. And so the reinforcement had to be added. Basically, the 3D print is a lost formwork. And you install the steel reinforcement and then cast a structural concrete inside. And this is how this technology is being used in almost all market cases today, is just simply as a lost formwork. After talking about the technologies, what I'd like to point out is that what is unique, or let's say what is common about all of these three technologies, the main ones related to concrete processing, smart dynamic casting, digital casting, and concrete extrusion, it all has to do primarily with the fact that they are dealing with continuous concrete processing. So in these processes, I would say in most digital fabrication processes with concrete, you have some universalities. That includes first that the concrete has to be delivered. It has to get to the point where it has to be placed. So it has to be generally done by pumping. So it has to be pumpable. Then it has to be placed and hold its shape. So I just call this placeability, because sometimes the concrete has to flow well to fill a mold, or sometimes in extrusion, for example, it has to be stiff enough so that it can hold its shape, so that then the next layer can come on top of it. And that is a very unique step. The concrete then has to have strength to support further layers that are going to be placed on top of it. And this is this is called in the field buildability. So schematically, they're seen here. On the left is the process for smart dynamic casting and digital casting, where you need it just to fill a mold. And on the right is concrete extrusion or 3D printing. First there is a pumping step, and then there is a placement step, and then the building step, where let's say for 3D printing, each layer has to harden a bit more to build strength so that the next layer comes on top of it and doesn't collapse it, and so on. And the same is for smart dynamic casting and digital casting. You can put the concrete in, and then it has to harden, because as the formwork slips up, it just collapses if it doesn't come out. And in the case also of digital casting, the formwork will break. What we state is that if you want to achieve structural scale heights in very fast processing times, let's say you want to 3D print a building in 24 hours, for example, you have to have absolutely some form of hydration control. And the reason for it is this. This graph gives you a concept of how strength builds up over time in a fresh cementitious material. First, there is some green strength, so it's fluid, and there is what is called normally in the field thixotropy. So some thixotropic buildup. Sometimes it's called a kind of green strength, and this is coming predominantly from flocculation processes between cement particles and some low-level hydration products being formed, but massive hydration hasn't started yet. And if you rely on this, the rate of this buildup is often called a thix. If you rely on this, it normally reaches a limit, and this limit normally doesn't let you build above much more than about 1/2 meter or 3/4 of a meter. And if you try to go above that limit, then you see what we see here with our more fluid concrete, so we don't get much more than 10 centimeters before it collapses. You get a collapse. So what that means then is that you have to initiate hydration, and to initiate hydration is some form of set control and the formation of massive hydration products, which then give you the strength buildup that you need. And this is done through the addition of an accelerator, typically. Now, accelerators are typically added to concrete right when you mix it in the batch mixer, and then transported to where they need to be transported and then placed. But what we have found in our systems is that you need to place it as, you need to add the accelerator as close to the point of placement as possible. So this is a schematic of our 3D printing process where we have a concrete pump. We have our nozzle, so that's where the concrete comes out, and then our robotic arm. So this is our 3D printer because it's all controlled here by a computer, the process. And then we have our accelerator pump, and our accelerator pump is adding concrete here, right at the point of placement in an inline mixer. And the reason for that is because if you don't add it at the point of placement, then you get buildup normally of accelerated and hardening material in your pumping line, and then eventually your process has to stop. We have developed a couple of printheads. On the left, you see our extrusion printhead, where we have some impellers that are mixing in the accelerator that we inject here before it comes out of the extruder. And here's our casting printhead, where we inject an accelerator before it comes out of a chute into the formwork. So there's some kind of sleeping concrete. We use we generally retard our concrete to get a longer open time. Add the accelerator, have an active mixing unit with a motor before out comes the activated concrete. And this is really the state of the art from industry as well. There's only there's really only 3 industrial players when it comes to very fast vertical build rates with the addition of accelerator close to the point of placement. Of course, the system from the startup in France, Extree, the Baumit system developed in Austria, and Sika, of course, has made a lot of headlines with their really great 3D printing system. But this is really what allows you to build at rates of anywhere from 1 to 5 to even 8 meters per hour vertically. Last about our methods I'd like to talk about is knitting as a method of digital fabrication with concrete. You might think, well, that's a bit strange. What is how can you knit with concrete? Well, you don't really knit concrete. The great thing about knitting is it allows you to create very nice, beautiful, bespoke shapes in space that you then have to concrete. So the idea behind Knitcrete and the student Mariana Popescu you saw on the previous slide who developed this concept has to do with first the generation of a structurally informed shape, and then there is a prefabrication of the knitting-based formwork that will then be tensioned in space. Well, you can then transport it to site in a backpack, and then it gets tensioned on site to form a specific shape in space, which then allows the application of the concrete to harden and then form a structure. And this allows the construction really of these long kind of arch spanning structures, which are difficult to produce without a lot of scaffolding. And this allows their production with minimal scaffolding. In that context, with that concept, Mariana and our PhD student, who's now a postdoc, Lex Reiter, produced this big demonstrator. Here's the shape formation. This is a demonstration that was done in Mexico City at an art museum there called Knit Candela. So this is the generation of the shape, and then the knit patterns. And then there's still scaffolding that needs to be formed, but it's very minimal. the amount, and none of the scaffolding is inside. You tension it in space and then apply the concrete. And this is the digital model of what it should look like. So this is the actual knitting process that took place. In the space of a couple of days, Lex and Mariana knitted out the formwork in 4 pieces. They rolled it up, and then they packed it into vacuum-sealed bags, put it in their luggage, and flew to Mexico City from Zurich. Scaffolding was constructed. They add tensioning rods so that the shape can be formed. Is almost fully formed. They wanted to add a bit of, porosity to the shape and put these balloons in. Now here comes the concreting part, where it was essentially developed by Lex, a series of stiffening layers. The first was a very rapid stiffening cement-based layer. Gave it the ability to withstand deformations of the application of the concrete, and also give a surface for the concrete to adhere. And now this is not the digital model anymore. Oh, I'm sorry. I'm sorry. So this is now no longer the digital model. This is the real thing. So the fidelity of the real structure to the digital model is really quite spectacular. Really great work done by Lex and Mariana. Okay, so. Enough of that. Now I'm close to the end of my talk, and I really wanted to discuss the issue of sustainability, because what you saw in all these demonstrators was the ability to create nice bespoke shapes. These shapes certainly will allow for the reduction of material usage through many different avenues. But it's really worth understanding if this technology is sustainable, or if it's sustainable yet. And I think that's something that means that we have to understand, what does sustainability mean in terms of environmental impact. And what we like to say is that environmental impact is a ratio or a quotient between the amount of concrete, let's say the amount of embodied CO2 per unit mass of concrete times the total amount of concrete that you use for a given structure. So let's imagine this bridge that's behind what I've written here as a structure. And if we use a total amount of concrete that's low, then we have a lower environmental impact. And if we use low amounts of embodied CO2 in our concrete, then we also have a lower environmental impact. And our environmental impact is then also inversely proportional to the service life. So if our service life is very long, then our structure stands longer, is in use longer, and we don't have to deconstruct it and renew it or renovate it or replace it after a long time. So when it comes to digital fabrication with concrete, of course, we want to decrease the top and increase the bottom as much as we can to lower overall environmental impact. And when it comes to digital fabrication with concrete, it turns out that we're using very, very high paste contents in our mixes and very, very high clinker contents overall. We have cement contents often in the range of 5 to 600. Even one of our first mixes had 800 kilograms of cement per cubic meter. So very, very high. And it's like this because of the processing. So I don't think that it's very sustainable with respect to this just yet. When it comes to the total amount, however, there's a lot of promise here. And that's because we have higher shape efficiency. We can create shapes which are not these boxy shapes that you're used to seeing. We can create curvature. And curvature generally will allow us better structural efficiency, which means that for lowering the total amount of material we use, I think that there is a lot of promise. But we still have the question of service life. So that's something that still needs a lot of research. The research has already started on it, and actually with all these layer interfaces, you could call them cold joints sometimes in 3D printed concretes. They can become cold joints when you wait too long between layers. Then we can have potentially serious problems with respect to durability. So this is still an open question and it's still being evaluated. And it's also worth pointing out that we want this to be a technology that is being used to lower the overall amount of material. And as it turns out, the main motivation for the putting in this technology, at least as seen by the companies that are doing it, is to replace concrete masonry and to replace masonry labor and formwork labor primarily. So it's productivity that's driving it. And if you're replacing, so this is coming from the website of Apiscore, which is a major, one of the more major 3D printing players right now. They essentially propose here to replace concrete masonry with 3D printed concrete. And 3D printed concrete, as we saw, is on a per unit basis much worse than standard concretes in terms of the kilograms of cement that are being used. So it seems that sustainability and productivity are incompatible at the moment with this. But I believe that there are many chances for these to merge and to complement each other. And I think it's up to us in the research community to make sure that that happens. So main challenges, we saw a lot of different methods, and I mentioned a lot of the challenges while I was describing them, and I'll just summarize them here. In cementitious material research, there's a lot of research. This has been most of the explosion of publications in the past 5 years, I would say. There's still cool and interesting questions with respect to hydration and its relationship to yield stress. And I believe that there still are a lot of questions that need to be answered in how the processing is impacting the properties and we cannot consider, I believe, 3D printed materials as normal concretes. We have to realize that it's a different material and really treat it as a different material and accept it as a construction material as a different material, because it really is fundamentally a different material. One thing I didn't mention here, which is worth mentioning, is that if you remove the formwork from the construction of concrete, one of the functions of formwork was to serve as a skin for curing. And when you remove it, you suddenly have issues related to shrinkage and drying shrinkage. And so curing becomes another issue that needs to be addressed. And it's also a topic that's underway in many research institutions in how to manage the lack of a formwork. Yes, and as I mentioned, sustainability is an issue, and sustainability related to the higher paste contents and higher clinker contents in your concretes. So to reduce paste, you can just use big aggregates and improve your mix design. Until now, coarse aggregates are not used generally in digital fabrication with concrete. Most mixes are with maximum grain sizes of 4 millimeters or less. So the inclusion of course aggregates, I think, is a major step that can be taken. There's a couple of 3D printing companies and demonstrations that are already doing it, but it needs to be integrated more into more technologies, especially with acceleration. And then, of course, the introduction of more supplementary cementitious materials to reduce overall clinker content. This is also being researched by many. Modeling is a very promising and important topic because every print is very expensive. You basically lose very often a day or more just to try to do a 3D print, and they're not always successful. In fact, in the very beginning, they're rarely successful. So you end up creating a lot of trash. And it would be much better to use modeling as a tool to ensure that a print will be successful. So the development of modeling tools, I think, is really quite important. And I mentioned, of course, on the horizon and actually underway now is durability. People are researching durability. Probably the biggest challenge, I would say, and I didn't talk about it a lot, is the challenge of reinforcement and integration of reinforcement. In fact, the processing of reinforcement, let's say the robotic processing of reinforcement, has been termed to me by an industry person as a real game changer. You know, they said, Tim, we can control concrete hydration fine, we can 3D print fine, but it's the reinforcement that's really the issue. And many people are saying this. So adapting processes to include reinforcement is a major problem. There's a lot of promise with multifunctionality and the multi-material printing. So let's say you could print an insulation as well as a concrete, a structural part. This is called by the guys in Eindhoven the concrete color printer. And I think this is a really cool concept. And then there's the link to manufacturing, where we have to really make sure that we're printing what we believe we are printing. And then finally, I would like to say that it's important to keep sustainability and productivity compatible, as I said a couple of slides ago. Well, I thank you for your patience. I'd like to acknowledge, of course, all the people who have worked on this topic over the years. Of course, Professor Flatt, who is one of the, of course, major players and is now actually one of the deputy directors of the NCCR, and he's responsible for a lot of what this great work that you've seen. So thank you for your attention, and I'm happy to take your questions.
Wangler? Are we ready now? Okay, thank you. Okay, thank you so much, Dr. Wangler, for this very nice and enlightening talk. And I have also learned a lot. Congratulations for all the great work you have been doing in your institution. We have a couple of questions from the audience. Now I would like to ask direct that questions to you. And the first question is from Mr. Alper Ulushan. And Mr. Ulushan's question is about the use of 3D printers in the space. So he would like to know that, in the future, 3D printers is presumed to be used to produce structures in space. And will concrete be the material that is going to be used to produce those structures? And if concrete is to be used, what kind of work will be done for processing of concrete under these conditions?
Yeah, yes, that's thanks for the question. It's a very interesting question. I have to admit that so of course 3D printing in space is a very hot topic. It's obviously going to be probably the way that we create structures while we're trying to colonize the moon or Mars. And the very, one of the first slides I had was of Barak Kushnevnis, and he much of his research was funded initially by NASA with this in mind, to somehow use some kind of additive manufacturing technology to construct structures in space. I don't believe that we would be able to use concrete as we have it here, or as we define it here on Earth in space, because concrete, of course, needs a lot of water, and water is something that you, at least on the moon, you don't have a lot of, for sure, and on Mars even there's finding enough water for hydration of concrete, at least the way that we have it here, is probably not an option. There have been, however, developments related to 3D printing with, they call it lunar regolith, which is some kind of simulated moon dust and rock, as well as 3D printing with Mars regolith. I believe, from what I've seen, and this is where my familiarity with the work on space is very limited. What I've seen is that on the moon, it's not going to be this kind of like 3D printing process, but some more kind of a sintering process that they would probably use. And on Mars, maybe it's some kind of, let's say, Mars concrete or Marscrete. You can probably find information on the recent competitions related to 3D printing with simulated Mars regolith online. They've done quite a lot of that in the United States, I believe, in the past years as well.
Thank you for your answer. I agree with you. It will be probably something quite different than the conventional concrete. There is another question from Mr. Özgür Çakır. Do you think accelerated carbonation process can be applicable for buildability during printing?
Okay, so so accelerated carbonation is something that is absolutely, I think, promising for 3D printing technology, actually, as a carbon sink or a way to reduce overall carbon. Because one thing that we have found is that all these interfaces, so those 3D printed columns that you saw have 2 kilometers of interfaces each. So with this kind of interfaces, you have generally a higher permeability, or sometimes you can have a higher permeability. There's a lot of research on how these interfaces form and their nature and under what conditions. In our case, we see that they carbonate very fast, much faster than the bulk concrete. And this is, of course, bad for standard concretes, especially if you're trying to use it as a concrete cover. But if you are in a prefabrication setting, then maybe it's something that you can take advantage of to speed up the process of carbonation. Now, to answer your question, if it can be used in terms of accelerating buildability, for this, I don't think so, but I can't say for sure, but I don't think so, because carbonation is a diffusion limited process. And it's of course accelerated under very often in prefabrication context in CO2 chambers. So you'd have to be printing inside one of these chambers, and then you're still limited by diffusion, which the diffusion time, of course, increases by a factor of 4 if you double the diffusion length. So it's, I think, in terms of during the process, which generally takes, those columns were printed in, 2 2 or 3 hours each. During the course of a process, I don't think that it can help much. But I would have to actually check the numbers to be sure.
Thank you, Tim. There is no other question from the audience. I would like to ask you a question, Tim.
Sure.
If you don't mind. One of the major drawbacks at the moment is the structural design. So there are no codes, and you have listed many good applications of 3D printing approach, and they are all quite different from each other. And from what I know, up until now, most of the time people have been using the standards used for Masonry structures, right? However, I know at the same time, many of the companies or the institutions that use that technology, they are having hard time regarding the issuing of building permits.
Yes.
So what do you know about this? How is the situation in Europe?
Well, it's just as difficult as it is everywhere else, I would say, because it's a new technology and things move slow in construction and the structural engineering space. With respect to codes and all this, I know that there are that the standards and the road to standardization was initiated maybe a couple of years ago at the international level. So for sure it hasn't propagated yet to the national level. I can speak to our specific experience with this DFAB house, and we're about to undertake a new project to 3D print a tower, also in the same mountain valley in Switzerland. And basically, it's one of these processes where you just have to get an exception. Where you have a structural engineering firm that will sign off on this as an exception, and very often what this also means is that you have to do a one-to-one test of a structure, which is very, very expensive. The bridge that I showed in one of the first slides from Eindhoven, they tested that on a one-to-one scale. So it's still a very expensive process. I think that the way that many people get around it now is that, and this is a very wasteful way, is that you just don't consider the 3D printed concrete at all. It's just considered as like a lost formwork.
That's what I know about this situation, and it's not only expensive. At the same time, very time consuming. You have to wait for like maybe months, right, for the permissions,
yes.
Up until you carry out all the experimental procedures.
Right. Yeah, and as we are in Switzerland, actually, we also have to even wait for the town, the people to vote. Yes.
Okay. Thank you so much, Tim. It's 9:10, so I think it's time to end that meeting. Thank you for your time and for this great seminar. Okay. And I hope to listen you, and I'm sure our audience thinks the same way. We hope to listen you soon again, maybe in Istanbul or in Turkey.
Yes, I would really enjoy that.
That would be really great. And before I come to the end of my speech, I also would like to acknowledge the Turkish Chamber of Civil Engineers for this good organization. And dear guests, thank you for joining us today. And I hope to meet you again soon for other meetings, for other great talks like Dr. Wangler's talk. Thank you. Have a good evening.
Thank you very much.